Hello? Hello? Okay, fine. Okay, so let me start. Okay, good evening, guys. This is Naveen Kumar. Uh, I am doing my PhD right now in IIC Bangalore. I'm about to complete my PhD. And so today we are going to discuss the uh, question and answer session for mechanical engineering, that is for ISRO examination, and we are going to discuss 2015 paper, and that too we are going to discuss the manufacturing part and manufacturing and production part. For this paper we have 26 questions, and I'm not sure how many marks, but yeah, we have 26 questions, and we are going to solve each question, and then we are going to discuss the options of it, in the sense like if you have a question we have four options, right? So it's not only the right answer, we are going to discuss and see what is happening with the other options as well, why the other options have been put, are they misleading you? So that kind of situations will be there, so they want to filter you with confusing options. So how to not get confused with that options, we'll be discussing all these things. Okay, hopefully hopeful with that you'll be enjoying the session. So let's start. So in the first question, we have this thing where there is a welding plate here. Okay, let me take the pointer. Okay, so there is a welding plate here, and it is having some kind of a butt joint here, and with an angle of 60, and the thickness is 3 mm here. Okay, so in the butt welding process, using arc welding, so they're going to fill, or they're going to join these plates using arc welding. The arc power is found to be, so let's write what is given. So that is a good habit, to write what is given first, right? While solving problems, that is one of the good habit, that you have to write what is given. Okay, so let me take this. So let's write what is given. What is given? Arc power is found to be 2.5 kilowatts, right? So let's write arc power. So P arc is equal to 2.5 kilowatts, right? Kilovolt ampere, sorry, we can write volt ampere is again watts, no problem. So kilovolt ampere. Good. Now the process is used to weld two steel plates, each of 3 mm thickness, as shown in the figure. So this is 3 mm thickness. So the thickness of each plate is 3 mm. So let's write thickness T is equal to 3 mm. Right? Next, it is assumed that the metal transfer is okay. Determine the maximum possible welding speed. So they're asking the question. So this is the question: maximum possible welding speed. So that is a question. It is assumed that the metal transfer is of short circuit type, and the arc is for 85% of the total time. In the sense, what they are saying is that during that 85% of the time only heat is generated. The rest of the time heat will not be generated. That is what they are saying it, because arc is the source of heat here, right? So 85% of the total time heat is generated. Okay, so in a sense I can write that percentage of time, or maybe I can say there is a factor, some factor C. That factor C is 85%. I can write 0.85. Okay, take alpha steel. This is coefficient of thermal expansion. So this material is steel and it will expand upon heat. So that is what it's saying. So alpha steel is 1.2 into the power of minus 5 meter per second, right? Let me take that. So let me write here, alpha steel is equal to 1.2 into 10 to the power of minus 5 meter square per second, right? And K steel, that is thermal conductivity, is 43.6 watt per meter centigrade, right? So thermal conductivity, the rate at which heat is transferring, is this, that is 43.6, right? Watt per meter per Kelvin, or some people even write as this. Per Kelvin is standard, but in the examination is given per centigrade. Anything is fine, no problem. Melting point of the steel is 1530 degrees centigrade. So melting point, so T melting, temperature melting is 1530 degrees centigrade, and ambient temperature is 30 degrees centigrade. I'll write TA ambient temperature is equal to 30 degrees centigrade. So what is the question? The question is determine maximum possible welding speed. Okay, so they're asking the weld speed. V weld is equal to how much? V is the weld speed. Okay, so now the thing is we have two things. One, we have some power source. Through that power source, we are able to send the input, right? The power source is there. The power source will give you will generate the heat, right? So now, but this power source is giving power for arc to get generated. That's why the power is arc power. So arc power is found to be 2.5 kilowatt ampere, right? So now the thing is, if we have 85% of the total time on, it means that arc will be generated only for 85%. In the sense, whatever the power is there, 85% of the power, that is this, 85% of this will be utilized for heating the material and depositing. I repeat, 85% of the arc power is utilized for melting the material and depositing here. Okay, so what is the heat input? Heat input is 0.85 times of that arc, right? So that is 2.5 kilowatt ampere. So I can write 2.5 kilowatts. So instead of writing 2.5 kilowatts, I'll convert that into watts if you want. So that will be easy. Let me do it here itself. Here itself, okay. I will write P arc is equal to 2.5 into 10 to the power of 3 watts. Let me do this here. This is into. Okay. So this is P arc, right? So this is 2.5 into 10 to the power of 3. If you do the calculation, anyone who can let me know what is the answer for this? Anyone who is there? If you can do the calculation, I'll be very happy for this. Okay, so the answer for this is 2125 watts. So this is one. So this is from our side, but they're asking the welding speed given all this information, right? So the another formula for this is the rate of the heat input, right? The heat input with the help of one formula in the terms of velocity, right? Heat input formula where this alpha, K steel, this all these things will be coming into picture. So that's why he has some formula in his mind. That's why he has given all this information. So this is uh, uh, with as a function of velocity or weld speed is equal to 8. This is a formula you have to remember. There's no other option. K steel thermal conductivity. The uh, change in temperature, or maybe I can say the temperature difference. It is delta T M, change in temperature for the till the melting point, into time, sorry, into the thickness, into there is one formula, that is 1 by 5 less velocity, weld velocity, into width of the steel or width of the plate divided by 4 into coefficient of thermal expansion. This is the important formula that you have to remember. Okay, good. Now this is 1 and this is 2. 1 should be equal to 2. Why? Because whatever the heat that is generated by the machine is 2.5 kilowatt. In that 85% of the time arc is established. So 85% of the arc means 85% of the power, that is 2.2125 watts. And this also is in watts. So we can equate these two, because whatever the heat input we are generating, we are assuming that it is going into the plate, or it is, we are assuming that it is going into the operation. We are not seeing any losses, but generally we have losses, but here we are not assuming any losses. So that's why 1 is equal to 2. So it is 2125 is equal to 8k delta Tm into T to 1 by 5 plus V into W. This is width. Okay. So here we don't have width. W is equal to width. So this width we have to calculate. What is that? We have to calculate. We'll see that, because based on that diagram here, we should be able to calculate that. We'll do that. So this is a VW by 4 alpha. Okay. So let's first calculate the width and then substitute all the values in this. Okay. So for calculating width, so let's go here. So this is A, B, 60 degrees here, and height is 3 mm. The thickness is 3 mm. Let's do that. I'll take in the middle part only. So this is A, B, right? And this is 60, right? And the height is 3 mm. Or thickness is 3 mm. And this is the width. What is the distance between A and B? Is width. Okay. Now this is a triangle, of course. So you can just divide this line, perpendicular line, and this is 90 degrees here, right? So let us take some point as O. O here. This point is O. Okay. So if you take triangle, and maybe you can take point C here. If you take triangle O, or maybe BOC, from triangle BOC, we can say that the length is there and this is 30 degrees, of course, right? So we can say that the tan, right, OB divided by OC is equal to tan 30, right? So from here, I can say OB is W by 2, right? Because this is half W by 2 divided by OC is 3 mm is equal to tan 30. Tan 30 is 1 by root 3, right? Right? So now you just find the W here. So W is equal to 2 into 3 divided by root 3. So W is equal to and one more thing here, it is mm and in mm. So but here all the things what they have given, this is meter, right? So we'll convert this into meter. So it will convert into 10 to the power of minus 3 meter, right? So if you do this calculation, it will be some 2 root 3, some 2 root 3, because this root 3, this will be cancelled and we'll get root 3 here, right? So this will be 2 root 3 into 10 to the power of minus 3 meters. Okay, now we got the width, and if you see thermal conductivity is there, change in temperature delta T is nothing but change in temperature, that is Tm melting minus Ta. Okay, so this will be 1530 minus 30, that is 1500. Okay, so we have delta Tm, thickness is there 3 mm, 1 by 5 plus velocity we have to find out, or welding speed we have to find out. Width also we have found out, that is 2 root 3 to the power of minus 3, and this thickness also you have to convert into meters. So we will write it here, that is 3 into 10 to the power of minus 3 meter. Okay, and alpha also is given, that is, so let's substitute and we'll find out the value of V. So let's do that. So 2125 is equal to 8 into thermal conductivity is how much? Thermal conductivity is 43.6 watt per meter. So 43.6 you can write. 43.6 into delta Tm is 1500. 1500 into thickness is 3 mm. 3 into 10 to the power of minus 3 meters. 3 into 10 to the power of minus 3 meters, right? Okay, let me do one thing. I will rewrite it because that will come off. So the equation will become bad because I'll write it here because this will come in between. Okay, so 2125, is it 2125? Yes, it's 2125 into is equal to 8 into 43.6 into 1500 into T is 3 into 10 to the power of minus 3 into 1 by 5 plus V, that is what we have to find out, variable V into width is 2 into 2 root 3 into 10 to the power of minus 3 divided by, right? Sorry, divided by 4 into alpha. 4 into alpha. Alpha is how much? 1.2 into the power of minus 5 meter square per second. 1.2 into 10 to the power of minus 5. So I'm not going to show the steps of the calculation. You can easily calculate. Only one thing you have to find, and that is what you have to find this. So please do the calculation. Hopefully you'll do the calculation, and the answer would be weld speed is equal to approximately 0.0159 meter per second. Units also will match, and this will be the answer. And this is your weld speed. Okay, so if you see the options, if you is there anyone who has any question? Okay, good. So if you see the options, option number D will fit perfect because 0.0156, but option number D will fit. Okay, so this is the right answer. Okay, okay, let me tick it, or maybe D is the right answer. Okay, good. Now let's go to the next question. So next question is, it's a simple one, very simple one. That is the effective number of lattice points in unit cell of simple cubic, body centered cubic, and face centered cubic lattices. So what is simple cubic? So I have put the figure here. It's a very simple question. Straightforwardly within seconds you can put if you know the answer. Right? So this is simple cubic. Whatever you are seeing here is simple cubic. And this is body centered cubic. So it's also known as BCC. Okay, okay, let me write BCC directly. Body centered cubic. And this is face centered cubic, FCC. This is simple cubic, SC. Now what are they asked? Why it is body centered cubic? Because in full unit cell, at body, at center, we have one unit cell. Here, at each face of the unit cell, we have one. So because we have 6 faces, 6 unit cells are there. But in simple cubic, if you cut, you have 1/8 portion left out here. In the sense like this cube, whatever you are seeing, this cut, the small cut, whatever you are seeing, is the 1/8 portion of the total atom here. Not there, it's here, right? It's here. Okay, so this is 1/8. Okay, so if you count how many are there here, 1 2 3, so we have 8 vertices, 8 vertices are there, so you can just calculate, right? So what are they asking is effective number of lattice points, right? So that effective number will come from what is the that amount of that radius or amount of that lattice point, or that the amount of the atom is being contributed to that unit cell. So if this is contributing 1/8, that will be contributing 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, like that, 8 into 1/8, right? So I'll write effective. So I'll write here effective lattice points, right? So effective lattice points. What can I do? So for this, for simple cubic, it is 1/8 into 8 will give you 1, right? Now see the BCC. Here also you have 1/8, 8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. But at center, full atom is getting inside. So that also is considered, right? So it is 1/8 into 8 plus 1 will give you 2. So 2 are the effective number of lattice points in BCC. In FCC also you have at vertices you have 8, so 1/8 contribution will be there for that. So 1/8 contribution from the vertices into 8 plus, you see at each face half of it is chopped off. So half inside like this, half inside, half inside, like that. 6 faces are there. So half contribution for the 6 faces. So 1 by 8 into 1, this is 1 plus 3, this will give you 4. So what are they asking? So for simple cubic, body centered cubic, and face centered cubic respectively. So what we got? We got 1. Okay, let me. We got 1, 2, and 4. So the option number B will fit here. That's it. It's very simple, right? Next. So what are thermosetting plastics here? So they're asking some question on materials here. So thermosetting plastics have in general. So let's go option by option and see what is right. First, let's discuss what are thermoplastics. Okay. So I'll tell you, thermoplastics are nothing but, okay, let's go to plastics. Let me discuss here in the next page. What are plastics? Plastics. So plastics are divided into two categories. One are thermoplastics and another is thermosetting plastics. I'll tell you what are these. Okay. So these plastics, when what are plastics? Plastics are some kind of a polymer. Polymers are, some kind of a long chain, carbon, hydrogen. All these big long chains are there, right? So in that we have two categories. So what are thermoplastics? Thermoplastics are nothing but the type of plastics that can be heated, and once we heat, what happens? They will become softer, right? And as they become softer, you'll be able to reshape them easily. You can mold them. It's like general plastic. When you have some plastic, no, you see that they'll be melted and then they will become very soft, right? And otherwise, so I can say heat. If you are heating, it becomes soft. If you are cooling, it becomes hard. So that is thermoplastic, right? So why this phenomenon is happening? So these are some polymer chains only, right? So I told you already these are polymer chains, long polymer chains. So these are not cross-linked. So there are some linkages. Let's not go into details. These are called not cross-linked. These are not cross-linked. Right? What are the examples for thermoplastics? You have so many: polyethylene, polystyrene, polypropylene. There are so many things. Let me write one or two. Polyethylene, polystyrene, etc., 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 etc. Right? In the same way, what are thermosetting plastics? The thermosetting plastic, it is setting. It is becoming hard when you're heating. So that is reverse, right? So when you're heating, right, the polymer chain, whatever is there. So these are polymer chains, man. Please remember that. Polymer chains, long polymer chains, they can say. Right? This polymer chains will undergo some chemical reaction, whatever it is, and there are some cross linkages that are there in this kind of thermosetting plastics. As we are heating it, they'll harden, right? That is important. They harden. This is soften, this is harden, and while cooling it will opposite, whatever it is. So these are cross linked. The chains are cross linked. Okay, and what are the examples for this? The examples for this can go so many things. So resins, some epoxy resins, there are so many things, etc., etc., etc. Okay, now let's go and visit our question. Thermosetting plastics have in general molecular chains that can slip one. So if at all they are having cross linked, they can't slip. So this is wrong. BA ceramic, wrong. Thermosetting plastics are long polymer chains, not ceramics. Wrong, right? So why have a monolithic crystal structure? Oh, this is very different, right? Crystal structures are crystalline in nature, not amorphous. So there is a difference between crystals and amorphous. Crystal opposite is amorphous. Amorphous systems. So crystals means regularly arranged patterns. So whatever we have seen in the previous one are crystal structures, regularly arranged, right? So amorphous are very randomly arranged. So plastics are not crystalline. So then we can easily cross this off. Obviously, one is left out. That is, they have no long range crystalline lattice structure. Okay. So here, what they're saying is that they have some structures, right, which are very long, and no is important. They are not long range crystalline structures. They are some kind of amorphous structures, right? This no is very important, right? Hence these answer. These are amorphous structures, okay? And this thermosetting plastics, no, this cross linking, whatever is there, they'll increase the strength and thermal stability. So this, whatever this cross linking, no, I'll write it here. It's very important. So improves strength and thermal stability. Okay, good. Now, so till now we have seen this about plastics. Now let's go to the next question. Silicon steel is widely used in silicon steel. Okay, let's go and see whether silicon is used in cutting tool, dies and punches, electrical industry, and so we'll see what are the different materials that are used in each of the option and select the right one. Okay, so let's go and discuss. Let's discuss. So the silicon steel is widely used. So let's see what are the materials that cutting tools are used. Okay. So for the cutting tools, let me write here itself. Let's not. Let me write here only. So for the cutting tools, what are the things that are used? Generally, silicon. I never have heard of silicon steel. High speed steel we have used. Right? HSS high speed steel we have used, or maybe some tungsten carbide, which are very hard. Tungsten carbide, right? So these are typically very common tools for cutting tools, which are having good hardness, right? Hardness is one of the property for cutting tools, right? And heat resistance is one of the property, right? Because when you are cutting tool, this huge amount of heat is generated between the workpiece and tool, so that material of tool should resist the heat, right? Otherwise, there's no point in making the tool, right? So there are so many properties, toughness, all these things are there, right? But of course, silicon steel, there's no point. There's nothing like that. We never use that. For dies and punches, we generally use some kind of a material where it is harder, right? It should not deform very fast. It should not get dented very fast. Dies and punches are used in punching machines, I know, punching and blanking machines, or maybe we can use it in extrusion, forging, rolling. All these places will be using dies and punches, right? So there we'll not be using silicon steel. We'll be using some kind of carbides, right? Carbides, or maybe some kind of tool steel. It's called tool steel, not silicon steel, tool steel. So what are the properties that are required here? The property that are required to withstand high pressure, right? Withstand high pressure, or maybe to withstand wear. All these things are there for this thing. And for electronic industry, we'll see. For electronic industry, Yes, silicon steel is used. So why silicon steel is used? Because silicon steel is having one nice property, right? That is called magnetic permeability, right? So magnetic permeability is one of the important property that is there for electronic industry, and that is provided by silicon steel, right? Silicon steel. Right? So what is magnetic permeability? Magnetic permeability is nothing but it's the measure of ability of the material to conduct the magnetic field, or how fast you can magnetize some material. So that is what is magnetic permeability, right? So there are some ferromagnetic materials, diamagnetic materials. There are so many materials. Let's not get into that. But mostly this electrical industry people will be using this magnetic permeability, and silicon. I mean, they will be having this high requirement of magnetic permeability. Because of that, we'll be using silicon steel. And where we'll be using this? This will be using in some kind of electric motors, right? Some transformers, right? Transformers, or maybe inductors, right? All this wiring is there, no? So in electric motors we'll be using silicon steel, right? And of course this will be the answer. And what are the things that are used in chemical industry? The chemical industries will not be using some kind of silicon steel, but they'll be using some stainless steel. Yeah, because they will store some kind of chemicals in that to avoid corrosion. Stainless steel, some other corrosion resistant steels will be used. So that is the answer. So main important thing is magnetic permeability. Because of magnetic permeability, silicon steel is used in electronic industry, electrical industry. Sorry. So that is the answer. Okay. Let's go. Which bond gives the softest bond? So this is they are talking in terms of grinding. Okay. So grinding wheel. They're talking about grinding wheel. Grinding is used for finishing operation, right? Finishing operation. Okay, fine. So now we have different bonds there: vitrified bond, resonite bond, silicate bond, shell-like bond, rubber bonds, metallic bond. There are so many bonds. Each bond is having their own properties that you have to remember. There is no other way. So what is that bond, right? That is very important, because in grinding wheel, you have some material and you have some bonding elements. So bonding elements, I'll write it in different color. This is bonding elements, some bonding elements. And the blue color ones are your abrasive particles. So I'll write these are abrasive particles, and this is your bonding. The bonding will decide whether the grinding wheel is tough, whether the grinding wheel is soft, whether the grinding wheel is hard, whether the grinding wheel is having some elasticity. There are so many things, okay, that you have to study. So basically, they're asking which is the softest bond. So we'll go option by option. Silicate bond. Yes, this provides softness. Okay, provides softness because of its material. Don't ask why. Okay, shell-like bond. The shell-like bond is having strong wheels, which has some good elasticity, or possessing good elasticity. elasticity. Right? Vitrified bond. These are strong and rigid, very commonly used. Strong and rigid, commonly used. Of course, option D is, there is no way option D is right, because every bond is having its own characteristic. So softness is given by silicate bond, and hence A is the right answer. Okay. So there are some other bonds like metallic bonds. Metallic bonds are used for some kind of diamond. When you're mixing diamond as your abrasive particle, the bonding material will be metallic, so that the bonding will be good. Rubber bonds for flexible materials, right? And there is resonant bond. Resonant bond is for good shock absorption, and some where it needs where the material is highly irregular, or maybe the material is very highly anisotropic, which is having different material properties. So there is a good shock that is getting from material to the wheel. The wheel has to take care of that. So resonant bond is used. Like that, so many bonds are there. So according to the question, silicate bond is the right answer. Okay, next. And eutectide steel consists of, okay, this is from iron carbide diagram, right? So iron carbide diagram. So let's see, I have put the iron carbide diagram here, and that is this. Okay. So in this, okay, let's see if you guys have any questions. Anyone who is there? Okay, no problem. Yes. Okay. So the question is eutectide steel consists of wholly pearlite, wholly austenite, pearlite, ferrite. First, we will see what is this pearlite, what is this austenite, what is this ferrite, cementite, all these things we'll see. Then we'll get to the answer. Okay. So if you see here, the ferrite is this alpha. This is alpha ferrite. Gamma austenite, alpha ferrite. Okay. And if you're cooling down, that gamma austenite will be converted. Okay, this is cementite. Okay, this is cementite. This is cementite. Okay. So if you see here, this gamma austenite is cooled down at this point at around 728 or 720 degrees centigrade. It's called Curie point. If you heard of, I hope you might have heard of that. It's called Curie point. Okay, it's around some 720. I don't remember the number. It's around some 728, I think. Yeah, it is Curie point. Maybe it is around that. I'm sorry for that. Curie point. Why it is called Curie point? Because actually, if you see, there is alpha, there is gamma. What about beta? You don't have beta, right? So the thing is, I think 727. I don't remember. This is 727 or 8. Whatever it is, remember that. Okay. I'll let approximately. Okay. So now, while these guys, the researchers are doing some experiments of heating this and cooling this and all this stuff, right? So what they have observed is that this alpha Fe, this alpha ferrite, is BCC in nature. But at Curie point, below Curie point, the material is not magnetic. Above Curie point, the material is magnetic, something like that. Okay. So because of that, they thought that there is some phase change at Curie point. Phase change in the sense like the change in structure. But this alpha ferrite is BCC in nature, and the when it is here, magnetic properties are changed. When you go from here to here, magnetic properties are changed when you're going from bottom to top or top to bottom, right? So they thought that there is some change happening, but there is no change in the structure. It is still BCC. and this is FCC. So as there is a change in structure, again they give the term as gamma. Okay, good. So let's not deviate from that. What the question is, eutectoid steel. Okay, so here in the diagram, if you see at this point, this perlite eutectoid they are saying, no, this is what is eutectide, and this is occurring at 0.8% of whatever the carbon percentage, and this is 0.8%, and that is what is eutectide. The zone here is hypoeutectide. Eutec, you sorry, eutectoid, and the zone here is hypereutectoid. At that point, eutectoid. Eutectoid. Okay. So that is what is this. So the answer is the eutectoid is wholly perlite. Why? This side you see alpha plus ferrite plus perlite. Here it is Fe3C plus radioperite plus perlite. But at this point, it is only perlite, wholly perlite. Wholly austenite is here, right? That is not answer. Eutectide is here, austenite is somewhere here, so there is no point austenite. Perlite and ferrite, it is not possible, right? Perlite and ferrite, it's not possible because it is hypo. It is not eutectide. It is this perlite and ferrite is hypoeutectide, right? And what is the other option? Perlite and cementite. Perlite and cementite is somewhere here. This one, right? This one. It is hyper. So hypoeutectide, hypereutectide. This is not at all possible, and this is the answer. Okay. This is a simple question. If you know the diagram properly, then it will be easy to answer this question. Okay. So there are some things that we can discuss more because it's a full big structure itself, right? So when you are stealing from this is called austenite phase, right? If you're cooling from austenite phase, a microstructure of perlite is observed, and that perlite is layered structure having some cementite. Cementite is Fe3 is having some perlite. Where perlite is, it is hypoelectric. Where cementite is, it is hyperelectric. So many are there. Okay, please try to see this figure. So this kind of questions are maybe the ISRO guys might not ask some complicated, might also ask, we don't know. So make sure that every topic is well understood. Material science is having very less weightage in mechanical. I don't know why, but it is one of the founding stones for mechanical engineering because everything starts from materials. You directly take the property of material and then we start doing the calculations. But if you understand how these material properties are generated, then we'll be able to make more sense while doing some kind of manufacturing or maybe design. Okay, it's very important. Okay, good. Let's proceed. Oh, okay. Now there is a theory question. Okay, there is some kind of a numerical question. Okay, what is it? 50 flat pieces. There are 50 flat pieces of 1 mm thick. So the thickness is inside. It's not visible here. And the initial dimensions are shown in figure on left side. So this is the initial dimension. So this is initial, and this is final dimension. Thickness is 1 mm, and we have to make 50 of this kind of samples, right? Shown in the figure on the right hand side. The cutter of diameter 25 mm has 10 teeth. Okay, let's write what is there, what is given. Number of samples to be generated, number of samples required are 50. Right? And the cutter diameter, okay, diameter of cutter is DC, is how much? 25 mm. Teeth has, okay, 25. I'll write teeth as people write, okay, I'll write as T only. I don't want to write as, Okay, let me write teeth only. Number of teeth is equal to 10, right? And rotates at 100 rpm. N is equal to 100 rpm, right? Horizontal feed of the table is 10 mm per minute. Horizontal feed is 10 mm per minute. Very good. And assuming single tooth in contact, the material removal rate will be, they're asking material removal rate, MRR. Okay. So it's a very simple question. If you understand the things that are happening here, it will be easy. So what is happening? You have some cutter, and this is your plate. It is starting from here and it is ending here, and it is removing some material there. That extra material is removed. That's the reason why your thickness has been reduced from, sorry, the height has been reduced from, or I can say width has been reduced from 30 to 25, and length is same. Thickness is T, that is 1 mm fixed. So they are asking MRR. So first we'll write the formula of MRR. What is MRR? Material removal rate is equal to volume of material removed divided by time of or time taken. Okay, time taken of that material to be removed from point 1 to point n, initial point to final point. But here, one more important point, we have 50 pieces. They're asking for 50 material removal rate for 50 pieces. So we can even multiply volume of material removed from 50 pieces. 50. This is very important. This is from here. Okay. So now the volume of material is how much? The volume of material is here. Simply we can write volume is LBH, right? LBH. So I can write volume is equal to L into B into thickness T, right? Good. Now, what is required here? Volume is this thing. Time taken we have to calculate. So time taken will be calculated from this, what you say, the data. That is diameter of cutter, teeth of cutter, rotation, speed, all these things are there. No, through that we should be able to take the time out of it. Okay, how do you take the time? For that, we have to go one by one. Okay, the cutter is rotating at 100 rpm, right? If the cutter is rotating at 100 rpm, there will be some kind of a, this is rotated at 100 rpm, right? There will be some kind of a tangential velocity, and that velocity of cutter is equal to pi into diameter of cutter into rpm n. This will give you the pi dn will give you velocity in minutes, mm per minutes, because your diameter is in mm, right? Isn't it mm only, right? 25 mm per minute. But if I divide it by 60, it will get mm per second. We are converting it mm per second. So calculate that. Pi into diameter is 25 into rpm is 100 divided by 60. You will get approximately 130.89 mm per second, right? Now volume we didn't calculate, so volume per piece, volume, this is per piece, okay, is lbh. What is l? It is 205. Okay, what is the volume removed? What is the volume removed, right? It is l is 205, length is traveled 205. How much width is being lost? Width is being lost is 30 and 25. Okay, so 30 minus 25 is width, so that is 5 into thickness is 1. So this will be 1025 mm cube. Okay, volume is there, velocity is there. From velocity we can we can calculate. Oh, I don't know where. Yeah, sorry. 1 minute. Where is? Okay, fine. Now, yeah, this is good. Good. Okay, I understand. So this is the velocity. Okay. From velocity, we can calculate. I don't know why we have calculated velocity. Let me check here. Yes, yeah. I understand why we have calculated the velocity here. Okay, 1 minute. Let me see why we have done this. Then we'll get to the point. I think there's no point of this. Why we are calculating? Nothing required like this. 1 minute. I think I should have calculated on beforehand, but yeah, 1 minute. So if you see, we want time. We got volume for each piece. We want time. So time is equal to. Oh, okay. So if you see here, it is traveling from here to here. Okay. So the part is traveling from here to here. And who is traveling? The workpiece is traveling. In milling, cutter will be at constant position. The base material will be moving from one point to another point. So this is moving. They gave table feed rate, that is 10 mm per minute. So if you start at this point, the cutter will reach this point and the velocity is 10 mm per minute. Okay. So length by velocity will give you time, right? This velocity is here f. Yeah, this is what is important. Yes. So this is the length of cut. Okay, LOC. Okay, let me write that. Length of cut by feet, table feet. Length of cut by table feet. The length of cut is 205 mm divided by 10. And this will be some 20.5 in minutes, or 20.5 into 60 seconds. Okay, 20.5 into 60 seconds. Okay, so now let's find out the MRR. Simple. We have all the things ready. We'll find out the MRR. That is volume of the material removed. Volume of the material removed is 1025 into 50 pieces divided by time taken is 20.5 into 60, right? And that will be around approximately 41.68 meter cube per second. Okay, so this, if you see, approximately it is 41.68, it is 41.7, hence the answer is C. Okay, hence the answer is C. So this is a small confusion here. I'm sorry for that, because table feed is important here. Table feed is important. This is the milling time here. Milling time, very important. Milling time. Length of cut divided by the table feed. Okay, good. Let's proceed. German silver contains. Okay, so the German silver is, they're saying it is silver, but it is a misnomer. This is a misnomer. Misnomer means misleading. In the sense, you think that silver will be there, but silver is not there in that. There is no silver content available in German silver. Actually, German silver will have some different materials like, zinc, copper, nickel. All these things are there. Okay, so German silver will not have silver at all. What does it contains? It contains copper, 60% of copper, 20% of nickel, and 20% of zinc approximately. These are all approximate values, don't take it for granted, but the ratio is almost same, right? And no silver. Hence the answer is D. You might ask, what is the reason behind putting this German silver? We don't know. Simply they might have. There was some reason. Maybe German silver will look like some silverish color. Because of that, they have put it. Okay, so it is used in different applications like some corrosion resistance in copper, nickel, zinc are there. No, so for appearance also German silver is used because of its silverish nature. Like jewelry, instruments which are having some decorative items, like this German silver will be used. Okay, so this is a very good, I mean kind of a misleading question, misnomer. Okay, next. Addition of coal dust to green molding sand is to improve. So if you're doing casting, if you have studied the casting, first we have to prepare the mold. Then only we'll pour the metal liquid into the mold, and then only it will get freezed. After that, we have to break the mold, and then we'll get the part. After that, we'll do some fettling operation, some post processing, sand blasting, that blasting. After that, only we'll be getting the final part, and that will be going for the secondary machining, the secondary manufacturing operation, that is your machining, right? So there is a big procedure for this casting. In that first stage, we'll be preparing molding sand. In the molding sand, there are some ingredients. We'll have some. What is molding sand having? Molding sand will consist of sand plus moisture, that is water, some clay, and some binding materials and additives. Sorry, some additives. Clay is binding material. Sorry, additives. And in these additives, we will add this coal dust. Why we are adding this coal dust? It will improve the molding sand property. And what is the property here? That is what they're asking. Right? So first we'll see whether it will improve permeability. What is permeability? The ability of fluid to pass through that mold. It means that it's some kind of a porous media where the fluid has to pass through the media like a sponge. If you pass some fluid or if you pass some air, it will go to the other side. Even our cloths are permeable, right? So some kind of materials which are having pores will have this property called permeability. But I don't see adding coal dust will improve the permeability. Right? It might, in some cases, it might reduce also. We don't know. Improve surface finish is one of the option. It looks right because when you have add this coal dust, when you add this coal dust, what happens? This is your uh, molding. Right? This is your molding sand. Let's say after making the molding sand, and coal dust also has been added to this. So this is molding sand. Let's say after preparing the mold cavity, right? When you pour the material, what happens at the edges? If you have sand dust added in this, at the edges, what will happen? When you immediately pour at this junction, there will be some gas that is formed because that heat of the material will burn this coal dust and some kind of a gas is generated. That gas will act as some thin barrier, or a thin film barrier, they say, so that it will avoid this will avoid the contact between your molding or the molten liquid and the molding sand. Why? Because it should avoid the turbulence and all, smoother flow will be there. I repeat, moldings, if you're adding coal dust into the molding sand, the coal dust will burn when molten liquid is added or poured. The gaseous form is formed because of the chemical reaction, because of the heating of coal dust. The thin barrier will avoid the contact between the molding sand and the liquid metal, making the casting flow smoother. Even after the freezing, you'll have a good surface finish. Good surface will be getting, not surface finish, some good surface without any wear, without any markings. That is important. Okay, so I can say surface finish also will be increased. Okay, so this is the answer. Okay, what is moldability? Moldability is nothing but the ability to hold the shape. How strong is this? How strong this mold is? If you're pouring molten metal, if molding sand is very weak, if your whatever the mold material or mold you have made is very weak, what is the point? It will completely make into different shape. Whatever the shape that you want, you have to get it. Just under the weight of molten liquid, it is getting deformed and all, not useful, right? So it is moldability is nothing but ability to hold the shape. Ability to hold the shape. Hold its shape, not the shape, its shape. Whose shape? Mold material shape. Its shape. Okay. What is green strength here? Green strength is nothing but when you are adding water, green strength comes from that moisture content. When you're adding moisture, the state in which the material is having moisture, that is called green sand, and the strength of that sand is called green strength. Okay, so there is no related to this cold dust. So surface finish is the right answer for that. Okay, good. Next is slush casting. Okay, let me take some water. We'll discuss. Okay, slush casting process is used to produce. So if you see here, first I'll tell you the process of slush casting, and then we'll see the options, and we'll discuss about the other options as well. Okay, so this is the slush casting. What is this? There is a mold cavity. Okay, let me take this. So there is some kind of a mold cavity, and you have some kind of a cavity here. You have poured some material into the cavity, and that is filled into the cavity, and wait for some time. As you're waiting for some time, the thickness is developed because solidification will happen from the edges. From the edges, some thickness is achieved. After some thickness is achieved, you invert it so that whatever the remaining unsolidified material will be drawn back into your some other place, and then you wait for some time. It is getting solid. Whatever the thickness that you have achieved is getting strong now. Initially it is softer here, right? Then obviously you get this kind of, from outer side you'll see like this, but inner it is hollow. So now hollow. So this is the procedure of slush casting. So slush casting is used for making hollow objects. Okay. So slush casting is used for making hollow object. That's the first option, direct evaporator. Then who will make intricate castings? Which procedure used for making intricate castings? I think you might know the answer. Investment casting. Intricate shapes, jewelry, all these things will be made by investment castings, complicated castings. Large size castings by sand casting. Very large size castings were made by sand castings. Right? Engine beds and all these things, machining beds, all will be made by this. So thin wall maybe by using some centrifugal castings. I'm not sure. Generally, they'll be making some centrifugal. Okay, good. Next. Castings of same material. Again, this is a numerical. So let's solve it. Castings, two castings are there, case 1 and case 2, having same metal, having the same surface area. One casting is of sphere, another is cube. What is the ratio of solidification time per sphere to the cube? Oh, this is a pretty straightforward question. Let's do that. So what is case 1? It's a sphere. And case 2 is cube. Right? What they're saying, surface area are same. Okay. So surface area of sphere. So surface area of 1 is sphere. Case 1, right? Is let us assume the surface area, let us take a sphere of radius r and a cube of side a. Surface area of cube of sphere is 4 pi r square. SA2 surface area of cube is a cube. Right? So they're saying both are same. Okay, let me erase this here. Right? Surface area 1 is equal to surface area 2. Right? So I can say 4 pi r square is equal to a cube. Right? So let it be like this. Let's do something after some time. Maybe I can take r in terms of a or a in terms of r. Anything is fine for me. So based on that, we'll see. Okay, maybe I can take a by r ratios. Anything is fine. Okay, we'll see that. Now, what is the ratio of solidification time of sphere to that of cube? So solidification time is given by solidification time T or TC is TS. Sorry, TS is given by K into volume by surface area whole square. This square is important. This square is important. K square is important. People will forget the square. They'll mess it up. Okay. So they're asking the ratio of solidification time of sphere to cube. So they're asking solidification time of sphere, that is 1, divided by solidification time of cube, that is 2. Right? This is 1 and this is 2. Isn't it? Yes or no? Sphere to cube. Okay. So this is K V1 by SA1 whole square divided by K into V2 by SA2 whole square. K gets cancelled. SA1, SA2 gets cancelled. What is left out? V1 by V2 by whole square. What is volume 1? Okay, we'll write volume. Volume 1 is 4 by 3 pi r cube. What is volume 2? Oh, surface area is not a cube, man. I'm sorry. Sorry. See where my mind is. So this is 6a square. Sorry. This is a cube. Okay. So this is 6a square. Yeah. Please correct this. Okay. Good. Now we have volumes. So what is the volume? Volume is of sphere is 4 pi r square by a cube whole square. That is what they're asking. Right? Let's go to the next page. That is Ts of sphere divided by Ts solidification time of cube is, so that is 4 pi r. Volume is 4 by 3 pi r cube. Sorry, why am writing all these things? 4 by 3 pi r cube. 4 by 3 pi r cube divided by a cube whole square. Okay. So if you see here from this relation, we can get some this thing. Maybe we can get the relationship between the R and A. Okay. So I'll write like this: A square. 1 minute. We'll write R square. R square by A square is equal to 6 by 4 pi. Okay, good. Okay, here we'll do some manipulation. That's a good thing. 4 by 3 pi whole square into R by A cube. I'll send square inside, cube outside. It is allowed. Okay, just to make sure this. Now from here I can write R by A whole square is 6 by 4 pi. Excellent, we can do that. So 4 by 3 pi whole square into, this is 6 by 4 pi cube. 6 by 4 pi whole cube. Right? So if you see what is left out, uh, 4 is left out. Let's do that. Okay. 4 into 4a is 16 pi square divided by 9 to 6 cube by 4 cube into pi cube. Okay. So am I making any mistake here? Okay, let's see the options. Okay. 4 pi r square by a cube, 4 by 3 pi square r by 3, 6 9 threes, 6 pi square. This 4 is left out there. This is pi 4. Okay, good. So let's not do this. Let's do this. So this is calculation I should have done before itself. This 4 square. This 4 square, pi square gone. Cube gone. So 6, 4, 36, 36. So that is 36 into 6 divided by 36 into pi. So 36. Oh, this is 6 by pi. Excellent. Okay, this is the answer. Sorry for the long calculation. So this is this ds of sphere solidification time of cube. Okay, so that is the answer. 6 by pi. B is answer. Okay, good. Plug gauges are used to measure. So what is plug gauge? So this is the plug gauge. If you zoom and see, this is go and no go. So by looking at the figure itself, you know that it is used for measuring the cylindrical bores, not taper bores. Okay. Spherical holes are measured by using some other techniques like coordinate measuring machine or like that. Okay. The cylindrical bores are very commonly used, like in limits and you will see limits, fits, and tolerances, right? So for a specific tolerance, you will put a go and no go, right, to check whether the bore that we have made is in right condition or not, or maybe up to the standard or not. So the go gauge will check the minimum limit, and the no go gauge will check the maximum limit. So this will check minimum limit, and this will check the maximum. Okay, so answer is B. Simple question. Okay, next. Resistance spot welding is performed on two plates of, okay, this is again numerical. Let's write what is given. A resist. Okay, let us see what is resistance. Okay, this is resistance spot welding. You have two electrodes, bottom is fixed, two plates, and first the electrons are coming in contact with the two plates. These are the two plates that have to be joined. Okay, then you apply some force, then you pass the current, when you pass the current, as there is some gap between these two plates, there's a gap between these two plates, and that gap is some kind of an air. As air is resistant to electricity that is being passed, because of that resistance, joule heating is happening. As joule heating is happening, there is some kind of material that is getting melted in between these two plates in the molten form. That is why it is molten liquid. And then you wait for some time so that the molten liquid is getting into solidified state. When molten liquid that is being formed here is getting solidified, it's called weld nugget, and then you remove the force. And this cycle is processed throughout the plate, and you get some kind of a bond that is formed inside. We can't even see, but the bond is formed already inside. Okay, that is what is called resistance spot welding. Okay, so let's see what is the question. Resistance was performed on two plates of 1.5 mm thickness, right? 1.5 mm thickness. So let's write what is given. 1 point, okay, I'll write here. Okay, thickness is 1.5 mm, right? And diameter of electrodes. So you see this diameter, this diameter. So this is the thickness, and this is the diameter of electrode. Is 6 mm. Okay, 6 mm. And using 1500 ampere current for time duration of 0.2 seconds. Okay, so current I is 15000 high current process ampere, and time, I'm not writing t because already for t thickness has been taken care of, so it is 0.25 seconds. 0.25 seconds. And then assuming the interface resistance to be 0.001, this is the air resistance, 0.001 ohms, 0001, right? Okay. R is 0.0001 ohms. Okay. Assume the interface resistance to be this thing. The heat generated is in the form of weld. Okay, what their simple question? Heat generation is what I want to know. It are called the heat is generated because of joule heating, right? So heat is generated due to joule heating. Joule heating. It's called. It is generated. It's called joule heating. Joule, nahin, joule heating. Joule heating. It's called joule heating. Heating, and the heat generated H. Heat generated H is I square R. Simple formula. What is I? 15000 into resistance as 0.0001 into time t. This is time. Okay, so time is 0.25 seconds. There is no point of thickness, not required. Extra information, that's it. Okay, so this is this. If you calculate, you'll get as 5625 watt second. Okay, watt per second, watt second. Okay. So that is what is simple question, very simple question. Okay, next, preheating before welding is done. Very good question. So you do preheating, you do post heating also. We'll discuss preheating. Okay. So preheating makes the steel softer. Yes, it's true, but that is not the purpose. To make the steel softer, we'll go and do the heat treatment. We'll not do preheating. Okay. You want to make the steel softer, you want to make the material softer, you go and do the heat treatment, annealing, softening the material, right? Why we'll go for preheating? So I think the option seems to be not relevant in this context. Okay. Burn away oil, grease, etc. from the place. Okay. So to clean the workpiece, preheating is not done, right? You will be using some kind of surfactants or some kind of cleaning operations with some kind of solvents. You pour some solvents and clean, or you use some cloth and clean at the end. But you will not preheat for cleaning the plate or from the burn away oil and grease. Okay. To prevent cold cracks. Yeah, this seems to be good. Why? So the main reason for this is preheating. Why you are preheating? So if you have a weld plate like this, your torch is here. You're preheating because of the flame. This is some preheating you're doing it. Already there is some kind of heater. It is heating here. You're going here, heating is happening. You're going in this direction. Why are heating? Because if you preheat, the what happens, the thermal gradients will be reduced, because suddenly heat is applied at the place, temperature is put more. Let's say if your flame temperature is around some 600 degrees centigrade and your ambient temperature is 30, suddenly you're putting 500 degrees centigrade on that plate. That's not good, right? So because of that, what happens when you are casting, there might be a chance that some kind of water or moisture trapped inside. We can't see that, and that no, it's not trapped. That moisture will be trapped, and when solidification is happening, there is this thing called hydrogen entrapment. Because of that hydrogen entrapment, if you're suddenly cooling it or suddenly heating it, right? So this hydrogen will lead to entrapment, will lead to some kind of a what do you say, cracking, right? So preheating is required, right? So it's called cold cracking also. Why? Because of this hydrogen entrapment, right? Because of this hydrogen entrapment, there might be a chance that cracking is happening. So to prevent cold cracks, preheating is performed. What is plate distortion? Plate distortion is because of the residual stresses. Okay. The distortion is because of the residual stresses. How can you avoid plate distortion? Plate distortion, you can use to avoid this. We can use this process called backstepping. It's very important. You should know this. Nobody knows it. Not nobody. Some people doesn't know it. Some people do not know it. Sorry. Okay. So backstepping is used to avoid. Backstepping is used. Okay. So what is backstepping? What you do? You have the weld, right? So instead of going straight like this, what I'll do? I'll do this part. Then I will do this part. Then I'll do this part. What do you say? Sorry, what you're doing? So you'll do like this, then like this, then like this. Instead of going straight like this, I'll do like this, like this, like this. This is called backstepping. Okay. So if you do that, plate distortion will be avoided. Okay. Or sometimes you can put all these things plate in proper clamping, use some jigs and all, and then you can avoid the plate distortion as well. Okay. So for this context, preheating is used to prevent the cold cracks. Very important. This backstepping is one of the procedure that is used to prevent the plate distortion. To prevent the plate distortion. Okay, backstepping. Good. Now next is the velocity of tool along the tool face is known as. Oh my god. Okay. So if you will draw the diagram first, and then we'll see what is along the tool face and all. So if you see, this is the tool, something like that, right? This is the tool, and this is your workpiece. So if you see, this is your chip, right? Right, right, and this is your uncut chip thickness. This is your chip velocity, PF, right? This is your shear velocity, VS, shearing, and this is your cutting velocity, PC, right? So this is your tool, this is your chip, right? And uncut chip thickness, T1. Right? This is your workpiece. Velocity along the tool, on the face, this is tool face, right? Velocity along the tool is chip velocity. VF is chip velocity. Okay. Shear velocity VS, chip velocity VF, cutting velocity VC. Okay. So the answer is chip velocity. Along the tool. Along the workpiece, cutting velocity. Along the shear plane, shear velocity. That's it. Simple. Okay. Good. Next, milling cutter. Okay, again numerical. Milling cutter is having, let's write what is given here itself. Okay, sorry. Milling cutter having 8 teeth. Okay. Okay, so let me write teeth is equal to 8. Rotating at RPM, N is equal to 150 RPM. Feet per tooth. So feet per tooth, I'll write FT is 0.1. This is feet per tooth. Per tooth. Okay, let me write per tooth only. Per tooth. So what they're asking the table speed. Very good question. Some confusion will be there, but you should not make any confusion in that. Okay. So there are feed per table, feed for table feed is there, feed per tooth is there. There are so many. Okay. So let's say FM is table feed. Table is there, milling cutter table in bottom. We have used table feed in the previous question. If we have solved it. Okay. The table feed will be in meter per mm per minute or mm per second, whatever it is. Whatever the diamond unit you have, you can do it. And there is another thing that is mm per revolution. For mm per revolution, normal feed. This is feed mm per revolution. Feed in mm per revolution. Mm per revolution means what? For one revolution of cutter, how much movement the table has moved on bottom. That is feed in mm per revolution. Table feed directly we can give. So if you want to relate these two, we can relate it like this. Fm is nothing but F into N. How? We just check the units. This is table feed FM is mm per minute, right? So this is mm per revolution, and this is revolution per minute, right? So you can directly cancel, and you can get mm per minute. Okay. So sometimes teeth also is given as Z, right? Teeth is denoted by Z. So if I want to calculate F, that is feed in mm per revolution, I can do like this: feed per tooth into number of teeth. So what is feed per tooth? Feed per tooth is let's write the units first and understand, then we'll do the formula. So what is feed per tooth? Feed per tooth, this is a feed per tooth, right? Feed per tooth is in They didn't give anything. What is a unit? They didn't give unit. Actually, it should be in mm per tooth. Okay, feet per tooth is mm per tooth. This is mm per tooth into tooth into teeth. Will give you feet mm per revolution. Why mm per revolution? Because all the teeth are converted. All the teeth. Let's say there are 8 teeth. 1, 2, 3, 4, 5, 6, 7, 8. So on completion of one rotation, then all the teeth will be covered. So teeth per revolution. For one revolution, 8 teeth. Second revolution, again 8 teeth. Third revolution, 8 teeth. So this tooth will be cancelled, and this will be given a member revolution. Hope you understood the concept. Again, otherwise, if you go back and listen again, you'll get the concept. Visualize it. Okay. So hope you got the difference between table feet in mm per revolution, and feet for tooth. Now, table speed in mm. They're asking table speed in mm per minute. They're asking FM here. Simple. They're asking FM. Right? So let's do that. FM. FM in mm per minute. They're asking this. What is that formula we have? Formula is F into N. Right? F into N. We know that F into N is FT into Z. Right? FT into Z. Into Z into N. That's it. Substitute there, you'll get the answer. What is FT? Feet per tooth is 0.1. Feet per tooth is 0.1, right? And the number of teeth is 8. 8. And revolutions is 150. That's it. You do the calculation, you get around 120 number. And that is the answer A. Okay, let's go to the next question. We have some water. So the next question is this. Try to read the question, we discuss. Okay. In ultrasonic machining, the material removal rate would be increasing, decreasing, increase, decrease, decrease, increase. So this is a complete ambiguous question. Ambiguous means he's not telling in which context. That is a problem. Okay. So we have to decide. Oh, in this context they're asking, but so I don't know. So I'll discuss all the contexts, and maybe generally the question they ask general questions in the sense like in most of the questions some repeated answer is there. So I'll take that answer, but it's very contextual, and that context is not provided. It's very ambiguous here to select the answer. Very ambiguous. Okay. So first, let's discuss what is ultrasonic machining. The ultrasonic machining is something like this. This is USM ultrasonic machining. Generally, if you attend our classes, we'll discuss the non-traditional machining process in a series, in the sense like in a step-by-step manner, where we'll discuss the electrochemical machining first, electric discharge machining, and then we'll be discussing the ultrasonic machining. Right? So why we are discussing in that order is there is some reason. So electrochemical machining needs conductive material. Electric discharge machining also will need electrically conductive materials. Both workpiece and tool all have to be electrically conductive because you are passing electricity in both the cases where ECM and EDM they say. But if your material is not electrically conductive like ceramics, right, you have to go for some kind of a mechanical operation, and that is what is this ultrasonic machining, where you have some kind of tip of the tool which is attached to some transducer, and it is attached to some kind of horn, and there is some kind of piezoelectric transducer that is try to oscillate, and that oscillation will disturb the environment in that space, and that environment is the abrasive particles. As the abrasive particles are disturbed because of the ultrasonic vibrations, the particles will get momentum, and that momentum will hit the material, and that material will be removed from that very minutely because of that momentum. Right? So as we proceed to move, the tool will displace downwards, and so that the workpiece will be removed as the tool is moving downwards direction, right? As the tool is proceeding in the downward direction. Okay. But here they're asking the material removal rate is increasing, decreasing. Why? Which context? I don't know. Okay, this is the question. I don't know whether this question is in the paper. Let's discuss all the contexts. Actually, the material removal rate will depend upon. So okay, right? MRR depends on so many factors. So many factors. Okay, it will depend upon power input, frequency of this vibration, abrasive size that is we are placing here, hardness of the workpiece, the concentration of slurry, more number of particles or less number of particles in the slurry, because slurry is what? Water mixed with some abrasives. How many abrasive particles are in there? So less or more? What is the size of that abrasive particle? So many are there. So in each of it, there is a different aspect for the MRR. So I can say frequency is one of the factor, frequency of the vibrations, right? And maybe I can say feed force. Feed force in the sense like how fast you are moving it downwards. That is feed force. Is one of the thing, or abrasive size is one of the thing, right? And abrasive concentration is another, uh, thing. Concentration, right? Sometimes workpiece hardness is one of the thing, right? Abrasive viscosities. There's so many things. So most of the time, if you see, as frequency is increasing, as frequency or amplitude, as this is amplitude and this is MRR, it will keep on increasing. It won't reduce. Right? But if you see for feed force, this is feed force F and this is MRR, it will increase and decrease. For abrasive size also, it will increase and decrease. Okay, why? Because abrasive size, if your abrasive size is very big, so if your abrasive sizes are big, then what will happen? Then as it is increasing, it should hit mass into velocity. Momentum will be very high and it will hit because the average is increasing, mass is increasing. But theoretically, it should increase. But what happens? There might be an interaction between the abrasive particles. That interactions might make the momentum loss in momentum. Because of that loss in momentum, proper amount of energy might not be utilized to remove the material. Okay, so it might decrease over the period of time. As you are keeping on increasing, the material removal rate might decrease. Abrasive concentration also same thing. It will increase and decrease. So mostly if you see, the material removal rate increase and decrease, increase and decrease, increase and decrease. Right? If you are taking only frequency, it will increase. Right? So we don't know. Not frequency, the amplitude, sorry. So that is the reason why it is ambiguous, but mostly it is increase and decrease. That's why I'm putting increase and decrease as the answer. It can increase, so decrease cannot be an answer. There is no possibility, but I have doubt in this. Maybe if it is in the context of some other thing, it will be increasing. Okay. Okay, good. Next is Again a numerical. It's a simple question. Two life of 10 hours is obtained when cutting with single point cutting tool, that is 16. Okay. Two life, right? The two life T is given as what is it? Okay, 10 hours. In corresponding to cutting speed is 63 meter per minute. Right. C constant is given C, that is 257.35. On doubling the velocity, the two life on the doubling the velocity. So this is case 1. Case 2 is V1 T1. So V2 is 2V1. Then they are asking what will be the T2. Simple question. This is Taylor two life equation. Right? So let's go and do that. Taylor two life equation. Two lives equation. So it is Vt power n is equal to constant. So we can take case 1, case 2. So obviously we can say V1 T1 to the power of n is equal to V2 T2 power of n. Right? So we can cancel off T1, T2, but we do not know the value of n. So to calculate the value of n, we can use this formula. That is, we have T, V, and C. So from here I can say V1 T1 n is equal to constant. So what is V1? V1 is 6310, right? 63 into 10 to the power of n is equal to, okay, 10 in what? It is in minute. We'll convert it to seconds. Okay, we'll convert it to oh, it is hours. Oh, okay. Here it is hours and it is minutes. So we'll convert this into minutes. So this is 10 into 60 minutes. Okay. Okay. So let's do this. 60 to the power of n is equal to 257.35. 257.35. Right. So it is you just calculate the value of n. I'm not doing it. Simply you can apply logarithm on both sides and do the stuff, and you'll get it. N is equal to approximately 0.22. Now we'll come back here. So it is Vt V1 T1 0.22, V2 T2 0.22. Right. So V1 is V1, V2 is 2V1, right? V1 T1 0.22, 2V1 T2 0.22. So this, so not that. So we can cancel this and this, and then I can do like this. That is T2 by T1. T2 by T1 is equal to 1 by 2. Okay. Okay, it's approximately 1 by 2. Am I making any mistake? Let's see here. I think I'm not making any mistake. Okay. So, okay, sorry, this is 0.22. From here, T2 is equal to T1 into 1 by 2 to the power of 1 by 0.22. So that is T1 is how much? 63. Is 63 into 1 by 2 into 1 by 0.22, and you'll get the answer approximately 25 point some 7 minutes. You can do the calculation, you'll get the answer, and that answer is B. Okay, simple VT power MC. But I don't think they'll provide the calculators. So if you see this kind of question, try to solve this question at the end. Don't try to solve, keep on solving this using some your own talent, because it takes so much of time, right? So see, this kind of questions you can easily answer. If you know it conceptually, you can easily answer. If you have this kind of simple questions like this, easily answer. So all are having the same marks, right? Hopefully they have same marks. So why do you want to waste much time on solving this complicated, all these things? If you don't have calculator, come at the end if you have time. That's the best thing. Okay. This question is easy, but the thing is they are tempting you to solve this question by wasting your time. If you're wasting your time, you don't have chance to look at other questions. So that's the reason why you come to these questions at the end if it is calculation intensive. So that is one of the my tip that you have to follow. Okay, please. Next. 3-to-1 method of jig of location in a jig or fixture would collectively restrict the workpiece in n degrees of freedom, where the value of n is what? Okay. So let's do the 3-to-1 principle. Okay, this is 3-to-1 principle. What is that? You have some kind of an object like this. Okay, let's have some kind of an object, and this is x, negative x, y, negative y. Okay, let's not do that. Let's just follow the thumb rule. So we'll do one thing: y, negative y, thumb rule. This is z, this is negative z. Okay, so we have positive. Already we have six movements. Positive exit can go, negative exit can go. Positive z, negative z. Positive y, negative y. 6 movements already there, right? X, positive x, negative x, positive y, negative y, positive z, negative z. Like that we have clockwise, counterclockwise against x, clockwise, counterclockwise against y, along y, clockwise and counterclockwise against z. X, c clockwise, x counterclockwise, y clockwise, y counterclockwise, z clockwise, z counterclockwise. There are total 12 degrees of freedom. Do you have? So they're asking if you're putting 2 pins and 1 pins to the mutually perpendicular thing, how many degrees of freedom will be restricted? That's a good question. Okay. So if you see, there are 3 pins that are put at the bottom. If you're putting 3 pins in the bottom, you can restrict approximately, you can restrict 5 degrees of freedom. We can calculate. If you're putting 3 pins at the bottom, you can't go down in z direction, isn't it? You can't go down in z direction, isn't it? And okay, how many degrees of freedom are restricted? I think 1. You can't go down in z direction if you're putting on bottom. If you're putting 2 pins across, right, then you can't go in negative, you can't go in y direction, you can't rotate in z direction. Like that, total 9 degrees. If you do all these things, 3 pins mutually perpendicular, 9 degrees of freedom are restricted. Very important. Okay, check it. Please check it. Take a book. Take a book. Place it on three fingers like this. You put fingers like this. 3 fingers. You put. Okay, put a book. So it cannot go inside your fingers. So let's say it is like minus negative y. So negative y is closed off. You can't go. You can lift. You can move in x direction. You can, but you can't rotate along x and y, right? So for here I can from here I can say that from 3 pins, 5 degrees of freedoms are arrested. 3 pins, right? Then 2 pins you are putting. Then 2. Right, I think. Is 3. Yeah, it is 3. Just check it. If you're putting one more pin perpendicular to that, you can restrict one more. So if you are, what I'm trying to say is, you're putting bottom 3 pins, 2 pins perpendicular to that, 1 pin perpendicular to this. So bottom 3 pins, left side 3 pins, 2 pins, and perpendicular to the bottom and left side you have one more side where you can put another pin. So three-dimensionally I'm unable to explain, but that is how it is. So I repeat again, bottom you put 3 pins. So for bottom perpendicularly you put 2 pins here. For bottom and the side pins you put one more pin here. That's it. With this 3, 2, 1, total 9 degrees of freedom are being restricted out of 12. So what about other 3? The other 3 are used to facilitate the place where you can put your workpiece into the facility, right? So that is what is the 3 to 1 principle. 3 pins, 2 pins, and 1 pin. All the 3 pins, all these 3 are perpendicular to each other. This, let's say this pin is kept in some xy plane. This will be put in yz. This will be zx, like that. Mutually perpendicular planes. Okay, good. Next. So during an orthogonal machining, okay, I think we will discuss this from the next class, because we have reached the time here. So let's close the session from here, because this is a little lengthier question, so it will take maybe some 10 minutes. So this kind of questions you should avoid solving in the beginning of your examination. Maybe this question will be in the first question. Don't try to keep on solving this question, because this is lengthy. So if you're not providing calculator, then it will be more difficult for you, right? So these questions you just put it as review, put it some kind of a symbol where you can come back and revisit at the end of the question paper. All the easy questions you scan through and put it, and then come back to the questions where you are having some critical thinking or maybe calculation intensive. So that is one of the good way to approach these kind of examinations, because these are intensively, I mean, wantingly, these kind of questions are placed inside this question paper, so that you will waste the time. As you waste the time, the others will. This is one of the way they filter the people. Okay, so please. I know this is easy. Sometimes it is easy, difficult. That is different. If it is easy, also if it is calculation intensive, I tell you, come back again. Don't solve it right away in the examination. Okay, so I have some examination tips I'll tell you at the end of our complete the question paper solving session. Okay, hopefully I hope this video is informative and useful. If at all you have any doubts, please do comment into the channel. I'll be able to answer them wisely. Thank you so much.